Thank you, Carol. So the picture up there sort of suggests that a gentleman will be giving the talk, so I had to at least provide the stick to at least indicate that there might be an opportunity like that. So tonight we'll look at the art of seeing at a distance, and we're going to parse that in a variety of ways. The seeing part, the art part, the glass part, and what have I forgotten? Oh, behind, that's actually also an important part of this. So if I were to tweak that, the series is behind the glass, but tonight will be behind the looking glass, or at least one of the looking glasses. So where are we going to start? Well, I think we'll start then in the summer of 1608, whereas my colleague put it in the summer of 1608, nobody had a telescope. In the summer of 1609, everyone had one. Now, how is that possible? Slight exaggeration, but there's an important element to what he's saying, that everyone who was anyone had one. Now, how could a technology that took so long to come about be spread so quickly? Well, we're going to explore that tonight. In honor of the 400th anniversary of the telescope in 2008, 2009, a group of people got together and said, you know, Alvin Helden was wrong. Everybody doesn't have one. Let's make a really cheap one so that everyone really can have one. And we just happen to have one of those here tonight. We can take a look at that. It assembles in a few minutes. And it kind of replicates what Galileo would have seen through his telescope as well. So there's a little art of seeing that's embodied in that box as well. That's easy to get, right? Because there's two icons there that convey pretty clear meaning. The turtle, very slow to cross the road, and the telescope. Now, this cartoon actually has an important function here. It tells us about what a telescope is. It's for seeing objects at a distance. Now, notice I didn't say it's for magnifying things, because a telescope isn't primarily about magnifying. It's about resolving things that are at a distance that you can't see with the naked eye. In this case, the turtles have a pretty vested interest in seeing things at a distance. But there's nothing about magnification in here. So, point number one about the telescope, it's about seeing things at a distance, not magnification. Point number two about a telescope, size makes a difference. And you see the $2, $6, and $8 one. Clearly, the bigger one is more powerful, but more powerful in what sense? Is it magnification? Well, Og, our caveman, seems to think it has something to do with it because the moon still looks the same. But he's wrong. The power of a telescope is about the aperture, the size, the light gathering part. So now think about our own eyes. The pupil of our eye is what takes in all the light. It's about 5 to 7 millimeters. Well, for my daughter, it might be 7 millimeters. For me, about 5. As you get older, the pupil doesn't stretch so much, so it doesn't quite open as much. Quarter, third of an inch, something like that. All the light has to come through that. That's what you process. A telescope has a much larger surface area. The opening, the aperture is much larger. It admits a lot more light. That is the second function of a telescope. It's light gathering. Again, not about magnification. It's about gathering light. And until about 100 years ago, how we gathered light was through the use of glass. Glass enabled us to collect light and do something with it. And that's the story we're going to take a look at tonight. All right, so the big picture, we're going to look at about 400 years just to set the stage. We're then going to focus on a 150-year period. As Carol said, my research is on the first 150 years of the telescope, ending by around 1750. And then we'll wrap up and look at some of the consequences of our exploration. All right, any questions? And if you can't hear me, I can't see you, so you can wave your hand, but you're out of luck. But you can yell. Right? And if there is something that you want a little clarification on, I'll try to see you and clarify, but there's a Q&A session afterwards as well. All right, so of course we begin with, well, who else? Galileo. Galileo didn't invent the telescope, but he was the first one to really put it to use in a way that everybody realized, hey, there's something new out there, or there's something out there that we didn't know before, and therefore is new, and it had serious, significant consequences. So we want to take a look at Galileo in a little detail. For now, we note it's two pieces of glass, one at this end and one at that end, just two small pieces of glass that revolutionized the world, set off the scientific revolution, and did all sorts of amazing things. Well, he discovered everything there was to discover with those two pieces of glass, and nobody discovered anything until about 1650 and the years after. Now, this is a complicated sketch, intentionally so. We have now, again, a piece of glass at this end, but now we have 1, 2, 3 over here. And to put them in the right place, to make them the right shape, this is not a trivial business. All right? Whereas Galileo's telescope was a matter of art, this really was a matter of science. You wouldn't get this by happenstance, by luck. And this enabled the astronomers of the day to see things that were impossible to see with Galileo's telescope. There really wasn't much improvement in the glass technology for about 100 years, and that's the reason for my research ending around 1750. The result here of these multiple lens eyepieces was uncovered, discovered, displayed in this really strange book that has the name of Oculus Enoch. Enoch being a character in the Old Testament who didn't die. And, well, you might think that this is a strange book, and you would be right. It's a very strange book. But here, hidden in there, is this nugget that shaped the history of the telescope. Now, we need to look at one fundamental property of glass that really bedeviled astronomers for that period ending in 1750. And that is a familiar property that you've seen before. And that is that glass bends light. But it bends light in a way that different colors bend by different amounts. So if we have a simple lens that is spherical in shape, white light comes in, and the blue light arrives at a focus at a shorter distance than the green or the red. Now, what does that result in? Well, it results in images that look like this, right? They have some blur, that's more spherical aberration, which in practice isn't really easy to distinguish from chromatic, but you get these colored fringes. Now, it's not a big problem if you're looking at terrestrial objects. It's annoying, but if you're looking at astronomical objects that are really small and have really, really fine details, this is a big problem because that color pattern blurs it all out. And remember, the point of the telescope was to look at distant objects and to resolve them clearly. This problem really messes up that task. So, one of the solutions is to make telescopes longer and longer and longer. This one from about 1675 is about 25, 27 feet long. All right. Not exactly, right? That's not going to be a solution. So that's a tough thing to figure out. And then, of course, if you're looking at astronomical objects that move, how you can move 27 feet? This is not a really great solution, right? Well, there's more to follow. In fact, Isaac Newton pronounced, you can't solve this problem of the colored fringe prismatic pattern except by making longer and longer telescopes. And of course, hey, Newton says it. It's got to be true, right? So, we have really long telescopes. Not just 25 feet long, 50 feet long, 100 feet long, 200 feet long, yes, even 300 feet long. They get so long that you don't have tubes anymore. You have a lens at one end, another lens at this end, and somehow you hope the skeleton in the middle keeps them in line. You have this whole system here. This is not easy to use, especially if it's windy. The size of that lens at the end is fairly large, so it's gathering a lot of light. The eyepiece is also fairly large. These are examples in Kassel in Germany, and they're one of a handful that still survive from the late 1600s. Spectacular stuff. I wonder if there's anybody around here who knows how to make glass and shape it like this. Maybe we could try to have one of these here and look at something in the distance. It'd be very interesting to try this. So what do you do when you do have these discs? Well, now you shave off the inside, make it flat, and you've got a nice lens. You've controlled the curvature on the outside. You've controlled the flat side, and you do that for both lenses. And you have spectacle pair, presuming that your eyes are about the same strength. You've got a nice pair of spectacles. Ingenious solution. Well, if you can shave off the inside of the lens, you can also shave off the outside, make a negative lens. For those of you who, for some inexplicable reason, are nearsighted or farsighted, you've got your choice of lenses, and there you are. Very ingenious. So what we're going to do is we're going to take a look at this pair of spectacles, see what you can see. And here is a test. We'll get rid of the specs. And now I have to explain what this is. So what we do is we shine light through a lens, and the light is parallel. We put a screen in front that has wires, a grid called a Ronchi grating. And if that lens is really good, and we look through it, the wires will look straight. And where the lens is defective, that line is going to go, well, something like those. Now here's the difference between spectacles and telescopes. Remember the pupil of your eye, 5 to 7 millimeters? That's all the region that you're going to use of those spectacle lenses too. So as long as the curvature on your spectacle is consistent for that 5 to 7 millimeters, you're going to have a clear image. And your eye can adjust a little bit. All right? So that's fairly straightforward. But for a telescope, it's quite different. The entire lens contributes to the image. And if you have defects at different places of the image, you're going to get a fuzzy pattern. And that's what we have on this side here. So here are the two spectacle lenses. We marry them up with an eyepiece, and we see what does the image look like. Now, it doesn't look terrible, right? But remember, the point of a telescope is to resolve and to sharpen things, right? Well, what we can do is try a little trick. And it's the trick that you would never think of doing. Instead of using the whole lens, you actually use only a part of the lens. In fact, you use a part of the lens where those lines are actually straight. Now look at the difference. Now if you use this lens as a telescope, woohoo, look at that. It works. Here is the invention of the telescope. You take spectacle lenses, you put them together, not going to work. You stop them down, you put them together, voila. Now we don't know exactly how that came about, but it's an accident. And that's the origin of the telescope. All right. So we started off with a statement in the summer of 1608, nobody had a telescope. That's because in October of 1608, or at the end of September, September 25, 1608, my sister's birthday, no coincidence there, this chap, Hans Lippershey, showed a telescope. Now it's where he showed this that's really interesting. There's a peace conference going on, right? Spain and the Netherlands are at war. There's a peace conference going on. And of all things, there is a contingent from Siam who is visiting. And they're spectators at this conference, ambassadors from Siam. that comes in importantly in just a moment. So here we have the actual patent application. Here is Hans Lippershey. The patent is October 1608, and blah, 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 Lippershey, blah, 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 telescope, blah, 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 blah. Anyway, there's the patent. So this is the first notice of the telescope. Now, how do we know about this? Remember those ambassadors of Siam? They actually published a summary of their visit to The Hague and published it in French. And this is how we know what happened. So I won't read it all, but here is the key notion. Spinola is the Spanish general. He sees this and says, he says to the prince, this is a problem because you will be able to see us from afar. To which the Lord Prince responded, we will prohibit our men from shooting at you. In other words, get out, we won't shoot at you because we can see you from a long distance. So the telescope, oddly enough, the first reference is not to astronomy, but it's to a military purpose, a terrestrial purpose. But thanks to our friends from Siam, we do know a little bit about the astronomical significance of this. Because underneath this arrow, for some reason, at the same time, stars that ordinarily can't be seen by our eyes because they're too small and feeble are able to be seen by means of this instrument. It's an aside, all right? Military purpose, and by the way, you can see some stars too. All right. So, some people pick up this idea. One of them is our friend Galileo, who is not the inventor, therefore, and he's also not the first person to actually do observations. We know there's at least half a dozen people who are making astronomical observations before Galileo. But Galileo invented the phrase, publish or perish. A few of his telescopes, well, this is actually kind of hard to say, but we're friends, so I'll say it. These instruments are in the Galileo Museum in Florence, just around the corner from the Uffizi. They are ascribed to Galileo, but there's no evidence connecting these to Galileo whatsoever. Absolutely no real documentation. The first documentation of one of them occurs in the 18th century, the other one in the 19th. So we don't know that they're actually connected to Galileo. But you didn't hear that from me. All right? But we're going to take a look at this frontispiece in a moment, just to see how the wily Galileo actually thought. But first we have to notice, what did Galileo actually see with his telescope? Now this turns out to be not so far off, as it turns out. Well, what did he actually see? He saw the moon surface as having craters and mountains, something that Aristotle said, nah, not the case. He saw moons going around Jupiter, and according to Aristotle, all motion must be centered on the Earth. And here was motion centered around another object. Bad problem for Aristotelian physics. He also looked at the constellation the Pleiades and said, by means of this instrument, things that are invisible to the naked eye are seen. Well, he didn't say that exactly, but you can see many things with this telescope that you can't see with the naked eye. The universe is much different than we had thought. What are we going to do? And two other observations. Somehow Saturn has this problem of, growing hips from time to time, and then they disappear. We don't know why. Venus goes through phases, something that couldn't happen on the Aristotelian or Ptolemaic system, but could happen according to the Copernican system, which had been announced in 1543, 60 years earlier. So this opened up a whole new universe, literally and figuratively, because now it wasn't by means of first principles of philosophy that you understood the universe. You actually did observations. You did experiments, experiences. And it's no surprise that the result of these observations were the microscope, which enabled you to see things you couldn't see otherwise. Thermometer, barometer, air pump, all of which use glass and were used to extend the senses and investigate the world in ways that hadn't been seen before. So literally, this is the beginning of modern science. Well, back to Galileo and his wily ways. He publishes this book, Sidereus Nuncius, in just a couple of months. Now, anybody who's tried to publish a book before, that's crazy, right? I mean, who publishes a book in just a couple of months? Well, he wasn't giving away much, because this is his description of a telescope. Here is an object, here is his telescope. And I don't know about you, but I've spent a long time studying telescopes. This doesn't tell me a whole lot. This didn't tell anybody anything. Now you'd think, he's rushing to get his observations into print to claim priority. Why doesn't he give away the secrets here? Well, it turns out, a few years earlier, he had a little problem with a student who took his course notes and published them and sold them. Galileo was a math teacher. He made his living actually teaching math and making instruments like these. In fact, he sort of invented, improved these devices, which are, well, here's a military geometric compass. This is a derivative of that called a sector. This leads to a slide rule. This is a computational device. This is a calculator that Galileo actually, if not invented, improved sufficiently that he made a lot of money off this. Well, his student published his class notes. Galileo sued, and he won. But it taught him the value of rushing into print. One of the people that he sued was a friend of his student, Simon Marius, who, well, did all sorts of things. He not only stole Galileo's idea and published his course notes, but in this book, On the Moons of Jupiter, in which he draws this telescope, which also doesn't tell you a whole lot. It tells you a little more than Galileo's, but no secrets there. He claimed priority for discovering the moons of Jupiter. And so Galileo and him got in a fight again over this. Now, Marius, in a way, won because the so-called Galilean moons, the Galilean satellites that go around Jupiter, the individual names of them, he gave them. All right, so a little tension there. Well, here's one of my favorite books and favorite frontispieces. It's Galileo's book on sunspots, and in it he alludes to this really nice story of how he sued and won. Now, if you look in the upper left corner, you see that? There's his little device. Now, this little Puto doesn't look like an ordinary Puto. He's a mean little guy. He's making sure he writes down his observations and his notes and gets them into print. Right? Nobody's messing with this guy. Well, what's going on in the upper right corner? Well, let me suggest something is going on there. It's not uncommon in frontispieces to have trumpets and fanfare announcing the latest discoveries, right? And the trumpet is actually going out, right? The sound goes out from the Puto to the world. In Galileo's frontispiece, thank you. It's inverted. The sound isn't going out, the light is going in, and it's going to the eye, not the mouth, and there's his observations. And at the very end, there is a lens. So Galileo has a really nice little twist to the trumpets. Still isn't telling us a whole lot about what's at the end of that device. For that, we have to turn to a contemporary, and we're really indebted to this guy because everything is packed into this little diagram. So I want to focus on that part of it right there. First of all, here is the eyeball. Here is the eyepiece lens. Here's the objective. I want to take a look at a few things here. First of all, flat on one side, convex. Got to get that right. On the other side. Now, this isn't from the ball technique. This is a different technique. To grind this, you actually take flat glass and remove this part. The flat part is really flat now, but you can control this curvature much better. So it's a change of technique. But this is actually more important. This little piece here. How much of the lens is being used? Only a very, very small part. Remember we showed that spectacle lens? You don't use the whole thing, you just use the center part. Aha. Well, when we take a look at telescopes from that early period, this is exactly what we see. Most of the lens is actually blocked off. You make the lens as big as possible to catch as much light, and then you stop it down as much as possible so you get a clear image. Now, to understand these shapes, we need to look not only at illustrations, but artwork in which telescopes appear. This one is in the Doria Pamphili in Rome, and it sheds a little light on that early history of the telescope. Now, what can you actually see? This is the surprising thing. Not a whole lot. All right? Whoops, I'll back up. Here is a clock that is only 50 feet away, looking through this telescope. Does that help you tell what time it is? Does that? Well, if you put the two together, maybe. But you can't see a whole lot. It's that small field of view. And that's why Galileo discovered everything that you could discover with those early telescopes. Because once he discovered a few things, there's nothing left that you could see with this telescope. You had to go to that new telescope with multiple lens eyepieces. So one of the things we're doing in the research is not just to find these telescopes, but to do optical tests. This one called the Foucault test that reveals a little bit about the shape of the glass, the bubbles in the glass, and with that Ronchi test, we can tell something about the optical quality. And so this turns out to be an important part of this and actually really painstaking because it can take, well, almost a day to get that. And what I'm working on is trying to develop an optical kit that reduces that time from a day to an afternoon to, well, maybe a few hours, or it'd be really nice, a few minutes. So when we started this project, we knew of about 8, maybe 9, and if you really pushed it, 10 telescopes made before 1650. Right now, we're up to about 25 to 30. So we've greatly increased the number that are known before 1650. And then we're cataloging the ones all the way up to 1750 and using images, illustrations, paintings, and whatnot. We're trying to identify the dates for them. All right, so here's one of those, a very early one. That's about the size of them. A beautiful object, beautiful decoration, and one little piece of ornamentation that will help us date it, maybe. These are actually all made out of paper. The tubes are made out of paper, rolls of paper, like cardboard tubes, like the center of toilet paper tubes or paper towel tubes, covered with leather to give it a little more strength, and then tooled with gold to make it look really, really nice. So another one, this one in Rome, a much larger one. Again, you see you're blocking off most of the glass in order to be able to see through it. And of course, recycled paper. So if we know what's written on the paper, we can date it. Right? Lots of paper. And this one actually uses a map of Rome that we can date. So we have some idea of how old that one is. Right? Another one, very small. This one actually is about the size of this remote, made by Uhrmacher, clockmaker. Now, this is probably my one moment of fame, so I have to tell you about it. In Berlin, there is a decorative arts museum, and this is the oldest dated telescope in the world. Dates from 1617. We know it because we have actually the name of the person who made it, the shipping information. I mean, it's pretty clear, 1617. Again, most of the lens is actually stopped down in that early fashion. Now, it's part of a decorative object, furniture known as a Kunstschrank. It's a miniature cabinet of curiosities. For those who couldn't afford a full museum, he built a little piece of furniture and collected stuff from around the world. Unfortunately, it's a war loss, so it doesn't survive. But we do have a painting. We know some information in it. And in one of those random neurons firing, I said, Kunstschrank. If there's one here, maybe there's another one somewhere else. And if there's one somewhere else, maybe it has a telescope. Well, a few days later, we were in Dresden. We saw, you guessed it, a Kunstschrank. We said, wow, we've got to take a look at this. And, well, we take a look at it, and we realized, whoa, wait a minute, I've seen that before. And we took a look closer at that paper. Here is the Kunsttrunk in Dresden. Here is the paper from the telescope in Berlin. We're thinking, we're onto something here. Well, sure enough, in the storeroom, neglected for 100 years or so, was this lovely object. As our Three Musketeers' lovely smiles indicate, woohoo, we found something that had previously been lost. Now, we take a look at the lens. Most of it gets covered. Here's the objective, here's the eyepiece, but it's this one I want to take a look at. Remember this drawing? We saw how the objective end, right, only a little bit is used. That's why you stop it down. Well, this turns out to be the other missing piece because the eyepiece is also only used a little bit. And now look at the shape of this. It's a little well, and only the central part actually functions. Well, when you take a look at the eyepiece, whoa, look at this. Not polished, and here's this nice deep central well. We know that's a really early one. So we're on the lookout for other objects that have these features. And we found a bunch of them, and we're looking at the optical properties. We also know that it's early because it's cut out and it's not polished and beveled and whatnot. All right, so 24 hours after finding that one, I was in Kassel, and you guessed it, somewhere in the deep, dark recesses that no one had looked in for hundreds of years, there was this object, and I said, oh my goodness, can we please look at that? And sure enough, it's another one of these early telescopes. Well, that sort of got the ball rolling, or whatever it does, and well, people start calling me now, hey, is this an early one? Well, no, it's not. I'll take it off your hands, though. Well, that didn't happen here because I can't say how much money they wanted for this, but it was a lot more than they should have been asking. And at this point, you'll be able to see why. What's off here? Because you can look through this and see an image. This side looks good, right? What about this? That's a replacement. Doesn't change the value at all, he says. Yes, I think it does. All right, so we're pretty much ready to wrap up. Through these longer telescopes, we see much more clearly. We can resolve what Saturn actually looks like. We can figure out the rings. We can do all sorts of things. And these telescopes, well, now they're discovering new things. And the question is, how do you make them? Well, you're making them with molds that you can actually control the curvature. These are all the surviving molds from the 17th century. But the pressing question is, there's a new observatory in town in Paris. Who's going to supply them? There are two candidates, two Italian candidates. One who makes gorgeous lenses that he signs on the edge like this. Very nice for him to date it. And another fellow by the name of Davini. They have a contest. And now it's up to you to see the art of seeing. All right? Alpha and Omega. Any idea where that comes from? Hang on, don't get ahead of me here. Beginning and the end, right? So you put this target at a distance, you look through your telescope. If you can see him with one telescope but not the other, the one telescope is better, right? Fairly straightforward. So, the trouble is, if you see alpha and, you don't have to see the rest, right? You know it's got to be omega. What about that second line? Nel mezzo del cammin di nostra vita. Any takers? Beginning of the Divine Comedy. Who said that? Oh, he works in the field. The beginning of the Divine Comedy. Any good Italian would know if you start nel mezzo del, I mean, you got the rest of the line, right? I mean, how hard is that? What about the next one? I thought so. I gotta have my cheat sheet. That one's impossible, so don't worry. Actually, it's not impossible. Petrarch. You who hear the sound in scattered rhymes. It's one of Petrarchan sonnet. Now, the next one, Here, Fracastoro of a strange coincidence. If you get that, I'll eat my hat. Francesco Berni. I don't know who that is. All right, what about this one? Can you see that? Aha. Well, this is another obscure person. Other than Stephen. Any ideas? Very good. It's a magic spell. Uttered where? Glenn, you can't look it up on your phone. I can see that far. This is the opening line of Canto 7 of Dante's Inferno. All right, now we're getting closer. Per far in leggiadra sua vendetta. Petrarch, another sonnet. And last but not least, Uscite di speranza voi centrare. It's close but not quite. Abandon all hope, you who enter here. Now, if you are an Italian competing in a contest and you see that, I don't think that's too hard. Same one, but now we put them side by side. Aha, with this telescope, I can see these lines. With this telescope, I can see those lines. Which telescope is better? The one on the right. 3 guesses who? Haha, I tricked you, I switched them. It's Campani. Well, it doesn't take long before you start having similar words and then completely random lines. Anybody see where this is going? All right. So the eye chart actually has its origins in the 17th century with testing telescopes. All right. So wrapping up. The telescope is an icon of lots of things. But see, here the joke is on, y'all. Because in the 17th century, you actually have telescopes that you look through the wrong end. Because they're designed to look through the big end, not the small end. Let that be a lesson to everyone. All right. Well, this particular collector has the oldest telescopes in the world. It has lots of these reverse taper ones. Here's a whole raft of them. You look through the big end, not the small end. And all sorts of maritime ones. These all mark that transition point in 1750. In fact, here we have threads underneath leather that are therefore threaded together. You have binoculars that are clearly works of art, and also maritime telescopes. All right, so to wrap up, since the time is up, we started off by looking at the problem of glass is that it doesn't focus light in a way that gives you clear images. The solution, we said, was this one, to put 2 different pieces of glass together. And the discovery was made by a lawyer by the name of Chester Moore Hall, who decided to put these 2 different kinds of glass together. He didn't know how to do it, so he subcontracted to, anybody want to guess who? James Mann. He subcontracted to another person. Anybody know who that is? I'll give you a clue. Edward Scarlett? I know, that's really a cheap joke, right? It's 8 o'clock, what can I say? All right? Unknowingly, they both weren't interested and subcontracted to the same person, George Bass, who figured out that these 2 nice pieces of glass really fit together and figured out the secret. And from that point on, telescopes entered the mass market. And it was no longer the purview and privilege of wealthy people, but you could mass produce them. And so now a telescope becomes an icon of knowledge for everybody. If you were anyone, you would have to know something about astronomy. It becomes a vision of looking in the wrong direction, right? A narrowness of vision. It also becomes a social commentary, and this is my favorite cartoon. We have the riffraff rising above his station in the middle class, being tutored by the wise eagle who says, to your right is the sign of Capricorn. But you know, you can't take the person above his station because right underneath his rather large nose, so to speak, his partner is off canoodling because he's so worried about social status he can't figure out that he's being cuckolded right under his nose. And last but not least, oh, this is where Paul Roberts would say brace, right? Brace. The transit of Venus. She is interested in the transit of Venus. His Venus interest is, somewhere in that area. The point of this is a fairly simple one. Telescopes were not just for looking at the heavens. They were interested in looking at heavenly bodies in the heavens and on Earth. And they were used to spy on people from the beginning. All right. So the gentleman of the day would have a telescope on his person. And I should say, this is the culmination of telescopes reaching to public audiences and being a very democratic instrument. But there's one telescope that you probably haven't noticed, and it's this one. Because this is actually a telescope. Right? At the very end, there is a 2X telescope that the gentlemen of the 18th and 19th century would have on hand, because at an opportune moment in the evening, when the conversation was lagging, this was a time to hold forth about the wonders of the heavens, divine order, to look really smart, or to check out Venus. Thank you.